There is a sharp debate over how software is written today. A new generation of tools is generating code from simple prompts, and many label the practice vibe coding. For purists, this is seen as a way to bypass the manual syntax and labor they believe is essential to mastering the craft. But engineers who have spent decades in the field recognize this tension. They have seen this specific backlash repeat across several generations of technology. William L. Weaver has spent 40 years designing scientific instruments. His career provides a roadmap to trace this cycle, from the early days of manual memory management to the automated labs of 2025. Weaver's experience suggests when a new tool is accused of being a shortcut for the lazy, it is often a necessary evolution to remove the friction between a researcher and their data. To understand that friction, we have to look at the environment Weaver entered in 1988. In those labs, the computer wasn't an assistant, it was a hurdle. Entry-level machines like the Sinclair ZX81 required incredible patience. They offered almost no resources, meaning every instruction had to be lean and perfectly placed. By graduate school, Weaver was coding in a language called Forth. It relied on a data stack. To do something as simple as adding two numbers, the programmer had to manually push the first value onto the stack, push the second, apply the operator, and then pull the result off to store it. For a single graduate experiment, Weaver hand-coded over 21,000 lines of these stack operations over 3 years. Every line of logic was a manual memory command. In this era, the scientist was subservient to the language. Time was spent micromanaging the computer's memory instead of analyzing the physics of the experiment. In 1993, while working at Wright-Patterson Air Force Base, Weaver discovered LabWindows CVI. It was a tool that provided an intelligent scaffolding for code, handling the low-level communication for instruments automatically. CVI generated the boilerplate code for things like user interface callbacks. Instead of writing pages of text just to tell the computer how to handle a mouse click, the software handled the syntax, letting the engineer focus on the logic. This shift enabled more complex physical science. Weaver could spend his time perfecting algorithms to track how a test article deformed under the high-speed buffeting of a wind tunnel. When hardware limitations blocked his data throughput, he used CVI to build a distributed network of 6 cameras running simultaneously. He produced 100,000 lines of production-ready code, a volume that would have been impossible with his previous tools. Purists at the time called these features a crutch, but for Weaver, the tool acted as an accelerant. It allowed him to master the system architecture rather than just the syntax. By 1999, Weaver pivoted to visual flowchart programming. He could take students with no coding background and have them building analysis systems in weeks. The visual blocks mapped directly to the way they thought about physical processes. But as the proprietary companies behind these tools grew and merged, their priorities changed. They began focusing on high-margin industrial clients, leading to what Weaver calls corporate drift. The practical results for his lab were painful. Support for flexible, low-cost hardware was removed, and academic licenses became increasingly bureaucratic and expensive. Research was grounded for 2 years, not by a failure of science, but by a war with the licensing servers and university IT administration. The barrier to discovery had changed shape again. The manual labor of the 80s had been replaced by the administrative friction of proprietary software. In 2025, Weaver abandoned the proprietary Windows ecosystem entirely. He rebuilt his lab using a resilient, layered stack designed to put control back in the hands of the researcher. This new architecture uses Debian Linux as its bedrock, with hardware control handled by Python and C++. At the top of this open stack sits the Google Antigravity framework. This design is resilient. If Google ever decides to end support for the AI framework, the underlying open-source logic remains functional. The researcher is no longer trapped by a single vendor's decisions. Decoupling his work from administrative lock-in allowed Weaver to resume his experiments after years of delay. Today, utilizing generative AI like Gemini 3.0 Pro feels like the discovery of CVI in 1993. It is a return to a tool that serves the scientist's intent. AI acts as a sophisticated form of autocomplete. It scaffolds web routes or optimizes C++ interrupts in seconds, handling the structural plumbing of the system. The AI is not solving the physics. The scientist still has to provide the intelligence and the goal. It is simply removing the modern version of that 1988 memory management problem. Ultimately, scientific mastery is defined by how well you understand the universe, not how well you memorize syntax. Modern tools are finally catching up, allowing researchers to spend less time on the machine and more time on the truth in the data.